Yes, welcome everyone. So a little bit about me, if things work along. So I work at Nordwave Cybersecurity, and there I do mostly red teaming, also some reverse engineering, and I really love automating things and finding a more efficient way to do stuff. And this project is also something that stems from trying to improve the efficiency for some part of our job. You can find me on GitHub as my handle. So today I'm going to tell you about shellcode compiling, and of course this is a topic that has been covered by many different people, but I aim to give you a bit of a different perspective on it. We'll dive into some background and then some problems and solutions that I ran into, and I will compare my solutions with solutions of previous work that I found. I will also give a demo of my tool and dive a bit more in depth into how the tool and the framework works. So existing work. So this project stems from something that I encountered during an engagement. I needed to write some shellcode in order to do some obfuscation about over that, and then run it into a company network. So I had to build some shellcode, and I researched a little bit in how I could do that, and I wasn't really satisfied with the ways that I found. So some existing work here by Print3M, From C to Shellcode. This was a really comprehensive guide on how to compile shellcode, but still there were some features that I didn't like. For example, every string that you use in your binary should be on the stack, so you should split it into characters and then put that into your code. So I really didn't like that. And also from Brute Tartel, there's a nice blog, but also here you see that he uses the string split into characters. There's also a framework that didn't use this, but if you look there at the limitations, this was really something that I couldn't really work with. Not possible to return the value of an API call, not possible to use pointers or buffers, so that won't really work for the shellcode that I wanted to use. Another example. And here I found a library that almost did everything. So here it uses normal strings. You can also see that it is able to use the Windows API. But what I didn't like about this framework is that they built basically their own compiler. I wanted to use existing compilers and build on top of that, so we use basically existing work. And what you also see here is that they manually specify the import user32, so they have to specify which library to import from. So that's also some pre-processing step that you need to do before you compile. Instead, what I want to do is compile exactly the same code that I would compile into a PE file into shellcode without having to do any changes. So that was the goal that I set out to achieve. We'll first dive into some background about how the whole compilation process works until we execute it in memory. So we start with a C file. I'm taking C as an example here. We compile it to an object file. Then this object file is processed by the linker to an executable, and that is loaded into memory by the Windows loader, and there also the DLLs are loaded into the process. So this is a very high overview of the whole process. So how do each of these steps look? For compilation, we have our source code, and that is transformed into the different sections that a process consists of. Well, in the object file, this looks as follows. So you can see that on the bottom we have the text segment with our assembly code. We have the data segment with the global variable 1. And we have the R data segment with our strings. Then also all of these segments are compiled into a PE file for Windows, for example. And during this linking step also the symbols are resolved to offsets. So first there's only the name of the function that you want to call, but then it needs to be resolved to where that function will actually be in memory when it is executed. And then there's loading. So the loader takes your PE file, loads it into memory, puts each of the segments at the right location, loads each of the DLLs into the process space as well, and then the program can actually execute. So how that looks in memory, if we enlarge the picture a little bit, we see our program image, and on the right we see that each of the segments is there with a specific offset. And remember this, because this is one of the problems that we will run into if we are actually doing shellcode. So then for compiling shellcode, a lot of compilers can actually do the basis for compiling shellcode. I analyzed some of the flags, but I didn't look them all up. I just copied them from a project for compiling shellcode. But OS is very nice. It optimizes for size. PIC is the most important flag, because that's actually the position independence that you need to be able to run something anywhere in memory. Usually we don't want the standard library, both because it's an enormous size and also because it's usually not compiled position independent, and it will be difficult to do that in shellcode. Some optimizations are not that useful for shellcode. So that's a bit of the background into shellcode compiling. So the problems with shellcode compiling and the solutions that were found previously and the solutions that I found during this project. So the first problem is that a compiled program has different sections, and these will be loaded into memory at different offsets. While for shellcode we have one big blob, so there are not really any offsets that we can use because we skip the whole loading step. So basically what we need to do, we need to put everything into one section. So solutions of existing work, that's where we see the splitting up into strings, is basically to put all strings into the text segment. And they do that by basically defining them as a char array, and during compilation they will be stored in the text segment instead of the rdata segment. But actually there is a way easier way to fix this. And here my colleague Michael Schrijver came along. He is a really knowledgeable guy, and I just asked him, hey, isn't there an easier way to do this? And he said, yeah, I have this project lying around and I haven't published it yet, and it has this linker file, maybe you can use it. So what this actually does is it sets the sections for .text, and basically it appends .text, .data, .rdata, .bss, whatever sections you want, into the same .text segment. And using this method, we basically let the linker do the work instead of having to do it pre-compiling. And everything will still be in that same text segment without having to do anything special. So I adapted this a little bit to work for MingW, to be able to compile for Windows. It doesn't support the output format binary, so I had to compile to an executable format and then extract the text segment using object copy. But the result is just the text segment that we want to use, which will be our shellcode. Then there's a second problem, basically the start function, because shellcode will start executing right at the start of your shellcode, and that is also the start of your text segment. But if you define functions like this, the start of your text segment will be the first function that is defined. So there's also solutions for this. And one solution that print3m uses is he defines a specific section called .func, and he puts every function in there except for the start function. And then during linking, you can first use the text segment and then use the func segment, and that way you ensure that one function will always be at the start. But I didn't want to change the source code. I want to do it in the linking stage. So my solution is to pass the function sections argument to a GCC. And what that basically does is it puts every function into its own section. So then you can easily say, I just want the function start at the start and then the rest of the text segment. So also this has a really nice solution in linker scripting. The next one, entry point main. You might have noticed that a lot of shellcode frameworks and also beacon object files, they don't compile from, they don't start running from the main function, but from something like Go or a different name, start. And that's probably because of this problem. When GCC compiles a function called main, it will automatically insert a -- main call. And this will do some startup handling in the GCC library. And well, it's basically something we don't want. I tried many ways to get this out, but well, this is what a lot of frameworks use, a different entry point. But what I, in the end, did is I just defined an assembly file that defines a really short stub for this main function, and then during compilation I just link with this assembly file, and that function is basically patched out. And problem 4, this is the hardest problem to solve, I guess. Linked libraries, because we don't have the loader stage. The libraries won't be linked automatically into our shellcode. So, of course, you can use load library and get proc address to load your functions, but it comes with a lot of boilerplate code. You have to do things like this for every function call that you want to do. Of course, you can abstract this away, but in the end, it is quite some work. Well, a solution that some frameworks use is they also define which library to import from, and also define the function signature in the shellcode itself. But we already have this function signature in the Windows header file, so why would we need to define this ourselves? So basically the only thing that we need is we need to be able to resolve a function name to which library does it belong to, and what is the function signature. So that's the solution that I did. So basically I create a library called winlib.c, and this implements a function stub, dynamically resolves this function, and then executes it. And then at linking stage, we can just use the normal Windows headers to get the function definition, and then later link it with this specific library to actually connect with the right implementation. Of course, we still need to be able to make this winlib.c function. And for that, I created a library that maps each of the Windows API function names to the exact definition and also the module that it is defined in. And then I first run the linker without the winlib.c. And of course, that will give you some linking errors, some undefined functions. In this example, winexec will not be defined. So we can easily parse that output, know which functions are not defined, put that into our winlib.c, and then link it again to get to our real output. So the next step, how did I create this Win32DB? You would think that mapping a function to a library and signature would be easy, because yeah, linkers do it all the time, and it usually happens automatically. But I could really not find a good source for this information readily available. So of course you have the MSDN documentation on the website, but those signatures are a bit adapted. They won't work directly in C, so that doesn't work. I tried PDB files, but to obtain the PDB files you need an exact file hash, and it's also not that easy to parse. There's not many good PDB parsing libraries that I could find. Then there's Win32 metadata. I looked at that one. It's a great option. Includes it's basically designed for exactly this purpose, but it does not include the MSV CRT, so the C runtime that Windows uses, and so that means functions like printf won't be defined. So it's a nice option, but it didn't completely work for my use case. In the end, I decided to just manually parse the header files and library files that are provided with MingW, and create a library based on that. So I did object dump on, for example, libkernel32, and that will list a couple of all of the symbols that are in that library, and then I just parse out all of the functions. Then I append each of these functions into a regular expression and run that over the header files, and then basically we get all of the definitions. So with a little bit of parsing, that will end us up with a nice JSON file that maps these function names to the exact definition, and we can do that per library. It's not the most beautiful of solutions. You can probably think of a better one, but at least we have in the end this library that we can use to really easily compile our stuff and link it with the right libraries. So now we get to the tool that I developed for this one. I call it Picklin Position Independent Code Linker, and you can find it on my GitHub. I'll also put this slide at the end. So basically, it takes this a piece of code like this, which you could normally compile to a position independent executable, to a PE file, but now also to a shellcode. So the output of Picklin looks as follows. Basically, it compiles the file itself. Then it links in some extra helper files that I put in the framework. Then it checks which functions are unresolved, compiles that into winlib.c, does the linking again, and then we have our final output. And then it also creates a loader, so we can easily test our shellcode and execute it in a executable. There's also some other features in the framework. To be able to call Windows API calls, we need to adjust the stack of our shellcode to make it actually work. So I copied this one from Manifestation and have also included that. And this was really easy to do also in the linking stage. I just put the start function that we defined here in the assembly code at the start of our text segment. So that will be the entry point for our shellcode, and that will execute the actual main function. And calling next shellcode, that is also a nice one. I also needed this during the assignment because I wanted to first call my own shellcode to do some dropping, configure persistence, and then I wanted to call my C2 shellcode. So basically I wanted to append those two together. And a really easy way to do this is to define a stub function called end. Using the linker, we will put that at the end of the text segment, and then we can just override that function, so override the last byte basically with whatever shellcode we want to call afterwards. So that makes this really versatile. And then also for resolving dynamic functions, in the previous example, you saw that I had to put the exact strings in for the library and the function name, but the Falcon Force team developed a nice project that resolves APIs, and it does it using a hash function. So that's already quite a better way to do this. Of course, there's a few caveats and improvements. So for Win32DB, I used the MingW headers, which are not completely in line with the Windows headers. But you could easily run the same project on the Windows headers and achieve with a better result. The parsing is very ad hoc. I didn't use a real C parser. I just did some parsing in Python. So there will probably be parsing errors, but it's more about the idea and the proof of concept in this stage. And currently I only have 4 DLLs implemented, the 4 DLLs that are used most commonly in Windows executables. But you could do the same trick for some different DLLs. And for Picklin, there's also some improvements. It's not yet battle tested. I used it basically for one project, for one piece of shellcode. So definitely do have a go at it if you want, but you might run into some things that need improvement. I also did not implement support for multiple payload files. In principle, this should not be a problem, but the framework currently doesn't account for it. The current version of winlib.c, it assumes that the DLL will already be loaded into the process. For kernel 32 and NTDLL, that's usually the case. But if you need a different DLL, you might have to call a load library still to ensure that it's actually in your process. And for OPSEC, you might want to consider using direct or indirect system calls to stay more under the radar for API hooking. And then while developing the framework, I thought, why stick to only C? Because now that we have this framework, we might be able to adapt it quite easily to different languages. So for example, Rust turned out to be a bit harder than I thought, but it was still possible. So Rust uses cargo for compilation. That adds the dependencies. Then it uses rustc to compile it to an object file. And then it does linking using GCC, and then ends up with an executable. So basically we want to replace this last step with piclin. So that's what I did. I wrote a cargo file, and you see that on the right I use a relocation model position independent code. That's a flag that Rust supports to make shellcode basically, or other position independent code. And then as the linker I used fake linker.sh, because it's really difficult to inject into the linker stage of Rust, because it's all just one monolithic process. But this fake linker basically takes all the linking argument that Rust provides. This is our actual input file, and it mangles the name completely, and it's almost not recognizable. But we just extract that to payload.o, and that will be our fake linking stage. And then we can do our real linking stage afterwards. So it's a bit of a dirty hack to be able to inject into the Rust linking stage. So how it looks like, we have here our Rust shellcode, which uses the most popular Rust Windows 32 API library. And you can just compile this to a normal executable as well. And you can call winexec, printf, things like that. And then we compile that using piclin. We do first the cargo run and then our own linker. And we end up with a position independent code that actually works. Because Zig is also getting more popular, as I try to do it there as well. So here I have a build file for Zig that includes the Zig Win32, one of the popular Windows 32 API libraries. And then I had to write a compile script that actually outputs a payload.o file instead of an executable. And then we can just link that as previously. Here I did have to define the printf function, and that's because this Win32 library is based on the Win32 metadata, which didn't include the C runtime. So that's one caveat of this library. But still, it works. We do the Zig build, we do our own linking, and we end up with shellcode that actually works. So basically, what I want to take home with you is this is a really nice proof of concept shellcode compiler that you can try to use. But more importantly, I want you to take home how this linker scripting works. You can do really a lot with the linking stage of compilation, and yeah, it's a powerful tool that you can use to your advantage. So that's the most important thing. Thank you for your attention.
Thank you very much for your talk. We actually have time for some questions.
Yeah.
Any questions in the audience?
So thanks for the talk. I have one question about the library, like the Win.
Win, I think Win32db, yeah.
Do you include that using the linker in your shellcode? Like, is it loaded in the shellcode, which you then load to a victim workstation, or is it something that happens during the linker stage and is then not included in your shellcode?
So if we look at, let's see, I have here the stub. So what we see here, the winlib.c, that is actually included in the shellcode. So each time a function is called, the function is resolved, and then it is executed. Well, while this is probably not the best way to do it, and in the current version it's a little bit better, you probably want to use direct system calls or indirect system calls, or build your own library. But I think it's the concept that matters, that we can inject this at linking time instead of having to do that before compiling, basically.
Thanks. Looks very cool.
Any other questions? No further questions? Then I would like to thank Jacob very much. And of course, also for you, we have the official OrangeCon cheese grater.
Yes, thanks a lot.
Thank you very much.
Yeah.